So I'm going to talk about Phoenix, this first iteration that was just released on GitHub. We have the pull request that's ongoing now, and what we have currently. I'm going to talk now about a very simple use case where Bob wants to send some dust to Alice. So he owns two nodes, like one obfuscated and transparent. So inside a single transaction, you can have any permutation of types of nodes. And he wants also to declare that Alice will receive not only a single node, but she will receive also any other set of nodes. So this is also possible. So how this works? Every node owns a secret key. So the secret key doesn't belong to Bob. It's tied to the node. I will explain more details on the next slides. And Alice can either use a single public key to be treated as a receiver, or can generate a specific public key for a specific transaction that she wants to perform. So Bob will define the transaction as as I'm specifying here, and there will be a 5 dust difference between the inputs that he stated and the outputs. These 5 dust difference, or any difference between the inputs and the outputs, will be defined as the fee for the miner. So this is how it is set up now. So for this transaction, the outputs will be, as I described, Bob will receive some change transactions. He can define the change transactions as well as he wishes. So in this case, the change is composed by 15 dust as transparent and 5 as obfuscated. So this implies that the sums of the inputs and the outputs must always be equal, including the fee. And the fee is treated as an output here. So every transaction item will contain the position of the node on the Merkle tree, the node itself as it will be stored on the public database, nullifier for that node, the value, the blind factor, and for the input, Bob will provide this secret key for that particular node for the transaction item. And on the output, we have like the node, how it's going to be stored as an unspent node to be used in the future, the value and the blinding factor. Both value, blinding factor, and the secret key are secret data. So these will be used only to create the proof. So after the proof is created, this data is cleaned from the node and the transactional items can be broadcasted without any security issues. So what will be broadcasted? The position, the node, and the nullifier. About the position, there is an open issue at the end, so I will talk about that. The transaction itself then will contain a set of inputs, set of outputs, and a transaction fee. Based on all of that, we have the zero knowledge circuit that will prove the consistency of this transaction. I will explain more details how this works. But when the block generator receives the transaction, he can inject his public key to the fee without compromising the proof. So the fee will have a particular situation there, because he cannot inject the public key in any other node, only on the fee. And if he do that, the proof will be verified normally with the commitments and the proof data that was generated by Bob and not by the block generator. So the block generator will not generate a proof. The proof will be generated inside the wallet. As for the blockchain, after the block generator injects his public key on the fee, he will, of course, build a block. And one of the transactions of that block will contain the R1CS proof data, the commitment points, the nullifiers, and the nodes. Both nullifiers and nodes will be sent to Merkle trees to grant the consistency of these items. And this block will be available for verifiers as it is. So any verifier can get this data and execute the verification of the proof, and he would not need anything else. This is the only data he needs to verify. If the transaction is consistent or not. So when the block generator proposes a block, anyone from this data can validate the consistency of this block. As for Alice, how she will understand that there was a transaction directed to her? She could monitor through the chain the incoming blocks, and with the view key, that's a derivation from the secret key, she can understand if she owns any of the nodes, if there is a message addressed to her. So basically, she tries to decrypt the node with the view key. And if she's successful, then she understands that this node belongs to her. And then she can add the relevant data of this node, like the block ID, etc., to the wallet. So basically, all of the nodes, once again, will have its own secret key if Alice wants. In this case, she uses the same secret key for both nodes. So it's her decision there. So after the block generator propagates the blocks, she can understand if Bob sent the money to her in the chain. So how's the data structure of the obfuscated node? We have as public data all of these items I listed here. Basically the type, the Merkle tree position, the randomness, the public key related to the randomness of that node. So if Bob provides his secret key and his public key to create a node, there will be an involved randomness also tied to the node itself. And the public key with R will be a combination between the secret key from Bob and the randomness of these nodes that will be generated by anyone. So in the case of the block generator, for example, he will inject his public key on the node. So he will change the PKR only. He will not change the commitment point, because the commitment point is related to the value of the node. And when we have the commitment point with a specific blinding factor, if we want to inject this commitment into a circuit without revealing the value, it's possible to do that if we have the correct blinding factor. The blinding factor is always encrypted because it could reveal the value, but it needs to be decrypted to use as input of another transaction. So this part here is related to the privacy of the value. So the block generator will only change the PKR. Therefore, he will not interfere in anything in the circuit. And this nonce is related to the encryption. So we have a public key, standard encryption. We are using X20 with poly here. And the blinding factor and the values are encrypted using these cryptographic functions. The transparent node have a very similar structure to the obfuscated node. The only difference is the value is not encrypted. All the other points are absolutely the same. So the commitment point still exists because this transaction will be injected into a circuit. So even if we don't encrypt the value, we need the commitment point for this value. And we also encrypt the blinding factor to comply with the standard of the obfuscated node. So there is no implication in that. Anyone can access the value of a transparent node, but nobody except the owner of the node can access the blinding factor that was used to create that. And I have 3 proof gadgets that were created to support with the circuit. I will describe them now. The first is the pre-image of the node. So basically, every node, we get all the public data of that node and hash into a scalar. It's a normal hash. And now we are using SHA-512 because Poseidon Sponge is not available yet. So as soon as it is available, we just change the function to Poseidon. And this will enforce that any node that's public that belongs to the blockchain that can be accessed by anyone, can be validated in the circuit. So what's the implication of that? If we define that the pre-image of a node, of a public node, is tied to a scalar, and this scalar is committed to the circuit, we can fetch the scalar publicly and inject on the circuit and verify if the original node that's being used on the circuit is the same node as the public database. So this way we prevent that some malicious transaction builder will use a different node to prove the circuit. So the nullifier consistency. The nullifier is just a hash with the SKR, the secret key related to R, and the position of the node in the Markov tree. So this will basically guarantee that the PKR is generated for the owner of the node that's building the transaction and using that node as an input. So if you don't know the secret key, you cannot generate a nullifier, and you cannot validate therefore, because of this gadget, you cannot validate the circuit. So this will guarantee that you can use any node as input only if you own the secret key, if you know the secret key of that node. So this is also a pre-image to the hash of the SKR and the position of the node. And also we validated the transaction balance. So we have the public commitment point of the nodes stored on the chain. So this is also a public information. So the verifiers will fetch this commitment point from the chain and inject this into the circuit to prevent also from a malicious transaction builder to manipulate the values. Since the Pedersen commitments for the bulletproofs are homomorphic, we can just sum these commitment points, and they will represent the sum of the values of the node. So we create basically two pairs of a pair of multipliers, one for inputs and one for outputs. So this implies that if I identify that a node is of type input, and this is a public information, I sum the commitment points to the multiplier of the inputs. And after I perform every sum, I constrain the difference to the commitment point again to guarantee that the difference of value is equal to the difference, is equal to the value of the node. So this way, we guarantee that we are adding only the value of the node. And by the end, if we just constrain the input versus the output, it's trivial to see that if this is not zero, then the node is not consistent. So this implies that the input equals the output. And this is fully implemented. So this part, there is no question about that.